Hello, good evening. In this session, we'll be talking about pressure at a point in fluid medium. A concept pressure will be built in this session. We'll see further. So here, uh, in pressure, we have to talk about Pascal's law, right? We should know what is pressure and then what is Pascal's law. Okay, pressure is nothing but a force per unit area. You have studied in strength of material the definition of stress. So, stress is also a force per unit area. Similarly, pressure is also force per unit area. For example, here there is an area that is 1 this way and then ds or delta s this way. So the area over here is delta s into 1. Over this area, the pressure intensity, it is called intensity because it is per unit area. So ps is acting. How much would be the force? The force would be ps multiplied by 1 into delta s. That would be the force. So here I have shown that force, right? ps into delta s into 1. So what I want to tell you here is the force divided by area is nothing but pressure. Force divided by area is also stress. Now when to use the words stress, when to use the word pressure? You have used this word pressure in day-to-day life like blood pressure, air pressure, right? So you can generalize the word pressure for fluids in the sense either gases or liquids. When you talk about, then the force per unit area can be referred to as pressure, whereas force per unit area in solids will be referred to as stress in strength of materials. So in this case, what the Pascal's law states, it states that the pressure at any point in the static fluid has the same magnitude in all the directions. What exactly this means we'll see in detail, right? First of all, fluid has to be stationary, it should not be moving. So static fluid, in the sense the fluid is not moving. And then if you consider a point in fluid medium, then the pressure in different directions will be the same. That is what it means. So direction coming into picture, right? That is to say magnitude as well as direction are coming into picture. So to say pressure is a vector. Pressure is a vector. It has got magnitude as well as direction. Now when we consider for the analysis a small piece, right, small at a point, so at point we'll consider as an object something like this, a prism, right? Here it is equilateral prism which is shown, but for the sake of analysis we should have a right angle prism. You can see here this is the front face of the prism. The bottom is in xy plane. You can observe here there is an xy plane. The bottom of the prism in xy plane with a dimension delta x along x direction. Along y direction we have taken 1, unit 1, so that it is easy for analysis, right? The base area of the prism becomes delta x into 1, and then left face of the area becomes 1 multiplied by this dimension which is chosen as delta z. So along z direction we got delta z, along x direction delta x, but along y direction we got only unit length or 1 as the. So now if I want to calculate the area on the left face, it will be 1 into delta z. Area on the bottom face will be 1 into delta x, and then this inclined face of the prism is delta s, which is an inclined length over here, delta s multiplied by 1. Sorry. Now if we want to consider forces, because when we want to apply conditions of equilibrium, we'll be using force summation, not stresses. Make a note of this. When we say sigma fx equal to 0 or sigma fy equal to 0, which you have studied in length in earlier semesters, that is sigma fx equal to 0 or sigma fy equal to 0, this is a force summation, not the stress summation. And here what we have is a pressure. So pressure, for example, if we say sigma fx equal to 0, we cannot just consider px. We have to consider what is the force which is acting on that phase, right? Then equilibrium of this particular body can be considered. So if I try to draw a free body diagram for this prism, the front face is shown over here as ABC. The same ABC is shown exactly in the front. Because of that, this three-dimensional view is missing here, right? Now from left we have a force px multiplied by delta z into 1. The area is delta z into 1. The intensity of the pressure is px. Because of that, the force becomes px into delta z into 1. From the bottom, there is a pressure of pz, and then area is delta x into 1. Because of that, the force becomes pz multiplied by delta x into 1. And then on this inclined phase, right, so the pressure intensity is ps, say, right, and then multiplied by the area gives you the force. Okay, now this force is along x direction, fine. This force is along y direction, fine, right? Now this is an inclined force with an angle at this particular point is alpha. Now this is alpha, corresponding angles. This will be 90 minus alpha. This will be 90 minus alpha. But this face and this line are perpendicular to each other because pressure always acts perpendicular to the face, right? So this angle becomes 90 minus alpha, that is to say alpha. Okay, when this is alpha, the component of the force along the direction adjacent to the angle is cos. Because of that, it is ps delta s into cos alpha, because force is ps delta s into cos alpha, a component that is. And then a component over here will be obviously sine, right? ps delta s into sine alpha. Now we can apply conditions of equilibrium sigma fx equal to 0, in which the rightward forces are considered positive, px delta z into 1, it is plus, and this is leftwards, that's why minus, ps delta s sine alpha equal to 0. From this we conclude, because delta s into sine alpha, again from the geometry, you know that this length is delta s and this is alpha. That's why opposite side delta s sine alpha, which is nothing but delta z, right? So that is substituted here, and then it cancels off, giving you a final result of px is nothing but ps. Okay, similarly sigma fy equal to 0, if I write here, if you look at this figure, free body diagram, the upward force pz into delta x is plus, and then you got a minus ps into delta s cos alpha. And then in addition to that, you have a weight of this particular piece of fluid, right? Weight will be nothing but volume multiplied by unit weight. Okay, I'll tell you the details here. So upward force of pz into delta x, this particular force I have written, plus minus this component ps delta s cos alpha, minus, right, the w, that is weight, will be written as look at this, delta x into delta z divided by 2 multiplied by unit weight of the material. Okay, now because it is a multiplication of two small elements, delta x into delta z, Because of that, what happens is it can be neglected, right? One confusing term may be this W. I'll better we'll call it as gamma, so that there is no confusion, because in earlier classes we have considered this as gamma, and then if you recall, W will be, or weight will be considered as gamma multiplied by volume. If you remember this expression, the same thing I have used. Instead of W, it should have been just gamma, that's all. So gamma multiplied by, this is a volume term, because what is volume of this element? It is area of the front face multiplied by 1. So volume is equal to front face area, that is delta x, delta z, delta x. It is difficult to write this way, but anyway I'll try. Delta z by 2, this is area, multiplied by the third dimension, this dimension, which is unity 1. So this gives you overall volume of the element, volume of the ABC not trapezium, ABC prism, right? So the volume, this is a volume. Actually here this into 1 is silent, or it has to be considered, right? Hardly it makes difference as far as the value is concerned. So gamma, the unit weight, multiplied by the volume gives you weight. But the idea here is, because of mathematical basis, delta x, delta z, two small quantities are getting multiplied by. That's why neglecting higher order two small terms, delta x, delta z, will be ending up with pz delta x, ps delta s cos alpha. You can see here, this is delta s. You got a right angle triangle, alpha is over here. This becomes, this particular length BC becomes delta s cos alpha. So delta s cos alpha will be written as delta x. Delta s cos alpha is written as delta x. It should have been delta x here. Okay, these two terms get cancelled, and then you will be ending up with pz is equal to ps. So what is the conclusion? At any fluid medium, whether you consider pressure this way, that way, all the pressure intensities are same. That is what the statement says. Hence, the pressure at a point, right, in a static fluid has the same magnitude in all the direction. That is what the Pascal's law. Okay, here pressure is shown, equally distributed pressure. Because of that, it is not one arrow, right? It is uniformly distributed over area. That's why it is multiple arrows are shown, and then the arrows are shown perpendicular to the faces. That is what you can observe. Okay. So conclusion is, when pressure P acts at any point in a fluid medium at rest, that's most important part, at rest, it is transmitted with equal magnitude in all the directions. Hence, the Pascal law is proved, which states that the pressure at any point in the static fluid medium has the same magnitude in all the directions. So P is always same in a particular, at a particular point in fluid. That is what we can remember now onwards. Okay, one more important concept one should know, that in earlier slides we have seen that pressure is taken perpendicular to the faces. So that concept one should know. Here there is a fluid medium, and then this is the top surface or free surface of the liquid, we can say, and generally we indicate the free surface with a triangle like that, and then couple of lines this way. So this indicates that this is open to atmospheric pressure, and then surface is perfectly horizontal. Always you know that the liquids will have a horizontal surface which is applied with atmospheric pressure from the top. So the pressure which will be acting on top of this surface is always atmospheric pressure. Okay, now this surface is perfectly horizontal. Now whenever pressure acts, that's what the point over here is, pressure acts on a surface, right? Fluid pressure on a surface, it always acts perpendicular to the surface. So here there is no depth of water, because of that the pressure is not acting. If you go little below, like this particular point, right? So here the pressure is acting because the depth of the fluid is less, the pressure acting is less. As you go down, the pressure is increasing. You go down, pressure is increasing. So at this particular point, because of this standing liquid, there is a pressure of so much. And if you go down, still the increase in pressure is there, increase in pressure is there, right? As the depth increases, the pressure increases. And the point to be observed here is the direction of the pressure on the surface is perpendicular. That is what you can make out here. Every arrow over here is perpendicular to the surface. You can just see here, this is also 90 degrees, this is 90 degrees, this is 90 degrees. So everywhere it is 90 degrees. So always the pressure acts perpendicular to the surface. This is a curved surface. It's a good example how the pressure continuously changes its direction and acts perpendicular to the surface. No component of this pressure will be trying to push the liquid down the line. Because of that, there is nothing like a sliding, right? So one more thing that I can tell you at this juncture is, suppose this is the immersed surface, a solid surface is immersed into a liquid. Now if you ask me, like, what is the pressure that will be acting at this point? Because of this depth, look at this, so much of depth of water is acting. Because of that, there will be some pressure which will be acting on this. Now look at this, the arrow I have drawn is perpendicular to the surface. So there is some intensity of pressure which will be acting in this direction. Fine. Now if you talk about this point, again there is more depth of liquid which will be there. Because of that, there will be more pressure which will be acting. But what is the direction? The direction is perpendicular to the surface, having more magnitude. Now in between also, if you consider, there will be a pressure which will be acting, and the direction is perpendicular to the surface. Now if you join all these points, it has to be a straight line because it is linearly varies. So this is called as a pressure diagram. Means on a vertical face, the pressure continuously changes linearly, right? This is linear variation because we'll be seeing in detail. The P is given by gamma into H. H is raised to 1. H means the depth, right? Gamma Y you can say, or gamma H you can say, right? Now one more thing is, if this particular surface is immersed at this point, let us say, or I'll hold it this way so that it is understood in a better manner. So the same, actually this is a surface which is something like that. Okay, now pressure at these horizontal points is this way, pressure at the bottom points are this way. Now this is also, you can imagine, there is a plate which is immersed this way. Now as there is no fluid, there is no pressure here. Intensity of pressure is, because of the fluid, is 0. Here also 0, here also 0, here also 0, here also 0, because there is no fluid which is on top of it. But if you go slightly below, there is a depth of fluid which is standing like that. Because of that, the pressure will be there, and as said, it is perpendicular to the surface. Now if you talk about this point, obviously here also there will be a pressure which will be perpendicular to the surface. Now if you talk about this point, again there will be a pressure. At this point there will be zero pressure. Now all these pressure intensities, if I join, again you will be getting a straight line. As I have told you, gamma multiplied by depth gives you intensity of pressure. So at any intermediate depth also you will be getting pressure intensity, right? Why it is gamma z, we'll be seeing it slightly in a later stage. Now what you should observe here is uh, pressure diagram that I have drawn over here or over here, right? These two pressure diagrams which show you a linear variation of the pressure, right? So this is called hydrostatic pressure distribution. Hydrostatic, why it is static? Because the fluid is not moving. Now hydrostatic pressure, how it varies? It varies linearly, right? A straight line variation. And then what is one more observation? As you go down below, the pressure intensity increases, right? As you go up in the fluid, the pressure decreases, and on the surface, the pressure because of the fluid will be zero. Of course there will be atmospheric pressure, right? So this is atmospheric pressure that will be acting uniformly, but because of fluid there won't be any pressure here. You have to go slightly below, right? Now on the surface it is like this. Now at this particular point I have shown there is a pressure here. Now if you talk a point somewhere there which is having an equal depth, now what is the pressure intensity? So here also the same pressure intensity as this. Now if I call it as a P with a suffix B indicating that it is a pressure at bottom PB. Now if any point which is having the same depth, right, in the fluid medium, because it is at the same level, now this particular considered point is also at the same depth. Now here also the pressure will be PB. Now what is the direction of the pressure? Just now we have seen that Pascal's law, it says that it is always same in all the directions. Now because of that, what happens is, if your immersed surface, now this is an immersed surface. Now if I put this plate here, let me choose the same red color. Now if I put this plate horizontally over here, horizontally like that, this is not a perfect horizontal, but you imagine that it is a horizontal surface. Now pressure at this particular point will be same as PB, but what is the change? The change is the direction in which the pressure is acting. It has to be perpendicular to the surface. Now if you ask over here how much is the pressure intensity, it is same because it is at the same depth, right? Now if you ask over here, the same PB will be acting. So here on a horizontal surface, the intensity of pressure is not changing. It is uniform distribution of the pressure. On horizontal surfaces, pressure because of the fluid will be uniform. It is not changing. So there is a concept that has to be kept in mind, right? So pressure will be uniform on horizontal surfaces, right? Now there is one more confusion. Like if you talk about this particular body or object, I have told you pressure is acting this way. Now how about the points on these, on this side of the surface? It is exactly the same, right? Here also it will be acting in the same way, right? That way. Now here for this particular element which is lying horizontal will also be acted upon the same pressure intensity this way. So here, because hardly there is a thickness, this will be almost in equilibrium. It won't be felt. I mean, this force will not be felt, right? It is the same amount of pressure which will be acting from the bottom towards the top, right? Because we have said that if you consider this as a point, the same pressure will be acting from there or same pressure will be acting from bottom, because we are considering thickness negligible or this as just a point. A point in a fluid medium will have the same intensity of pressure. Now, how it acts, that's most important thing that we are trying to emphasize here, that the pressure will be always perpendicular to the surface that is in contact. Okay, here I think we'll stop. We'll discuss further afterwards. Thank you.